Okay, let's get started. Today we're going to speak about evaporators, also known as concentrators. And what's an evaporator? Evaporators are used to remove liquid from something, remove water, out of a liquid as a way to concentrate it. So why would somebody be doing that? So I'll give you two examples, which is what we'll work with while we're talking today. One is if you have, the text didn't come out good over there, but you have grape juice, that's single strength grape juice. It takes up this much volume, and if you concentrate it by boiling the water out of it, then all of a sudden it's going to take up that much less space. It's good for transportation and for storage because it's taking so much less space. Or another example is, the other example we're going to use is if you evaporate milk. It's called evaporated milk, so you could buy it as evaporated milk. Not so common in the United States for people to use that, but basically when you evaporate milk, you're boiling water out of the milk in order so that it will be more concentrated. For milk, the main use that we have for it when we do it for milk is that we would, it's a preparation for spray drying. You want to spray dry the milk. You want to turn the milk into a powder. So you have to remove all the water out of it. You have to get all the water out of it. So the way you're going to get the water out of it, you could spray dry the whole thing, but that would take a lot of energy. So he said you first concentrate it to get out a lot of the water, and then you, what?
Just that's what you started.
I did. You concentrate to get a lot of the water out, of it, and then you get a lot of the water out of it, and then you spray dry to get the rest of the water out of it. Okay, that's how you do it. So those are the examples we're going to use. Nothing to do with what we're talking about today, but there is another way to use a concentrator is when you make salt, when you mine salt out of the ground and you pull the water, you get it out of the ground by flooding the caves with water, and then you concentrate, boil that, basically boil it all out. There's a Hashgachah question about that. Okay, you can read what I wrote about that if you want one day. The Hashgachah question about cooking the salt. Okay, anyhow, so we're going to use those examples of grape juice and water. Obviously, those are sensitive for us. Grape juice is being non-kosher, and milk because of milk. Okay, so how does it work?
You mean it's relevant for anything that goes in an evaporator because maybe this for those ingredients too.
I'm just saying.
For chicken soup, for that matter.
Correct. Not so common to use it for chicken soup. Yes, it could use chicken. You can use it for lots of different things. For our examples, we could use grape juice and.
So you're focusing not on evaporators. You're focusing on the grape juice and
No,
milk.
on evaporators. I'm just using when we're going to talk about how they use them. We're going to use those as our examples as we're talking about.
Are you supposed to add water to evaporate the milk? Like it's like concentrate?
Mm-hmm. Yeah. But again, for most of us, the use an evaporator to evaporate milk is a step before we spray dry it. Okay, it's the step beforehand. We evaporate so that we can spray dry it, just so we get a lot of the water out, so that the spray dryer has less work to do. That's for efficiency.
And is that a retail product right there?
Yes, that's a retail.
I've never seen. Never made it.
Right, because you eat chlovisol, so you've never seen it. And I mentioned already that in the United States it's not common to eat evaporated milk.
It's one of the ingredients.
Is there a different ingredient that I can just relate to that it's evaporated as a retail product?
So like if you have grape juice from concentrate, so you have
It's a retail product. It's not for consumers.
That somebody would have an evaporated concentrated product.
It's more for commercial.
Yeah, I mean the machinery we're going to talk about is very commercial. You'll see
But
it.
even as ingredients, the consumers they're not going to see it.
No, but we're not talking about the ingredient. We're talking about the equipment, the evaporator, not the evaporated. You know, the evaporator, the machine. Okay, so yes, upstairs Sean has the evaporated water. Okay, so how does it work? So the basic idea, we'll get into details in a second. The basic idea is that the water boils at a lower temperature than the other thing, what we call the solids. Okay, so if you heat it up, you get the water out, and that leaves behind something thicker, like a syrup, that you're going to be left behind with this thick syrup which is reasonably liquid, but it's much more viscous than what you had started with originally.
I just have one quick question. Single strength is just regular. Right?
It's regular. Mm-hmm.
I
Single strength is the original, as how it came out of the tree. Okay, so you could do this in a pot. Okay, you could boil up a pot of water in your house and just boil the grape juice in your house, and eventually it'll get thicker and thicker as you boil the water out and leave the grape juice behind.
Well, that will compromise the quality, won't it?
Yeah, we're going to pass that in a second. But an evaporator is a much more complicated device that does that in a way more efficient way than just boiling it up in a big pot. Okay, and that's what we're going to talk about. Okay, now the way the evaporators take advantage of a piece of, we'll call physics. I don't know what the right word to describe this is. Okay, and that is, as you increase vacuum, otherwise known as decreasing the pressure, those are the same thing. Increasing to make the stronger vacuum means that less pressure. Okay, as you do those, the boiling point goes down. Okay, as you have more vacuum, or another way of saying it is, you have less pressure, the boiling point goes down. Okay, so like for example, when I was in a factory, that was whatever reason why they were doing this, and they were essentially evaporating juice. The pressure was very strong. The pot, the kettle that they were doing it in, the device they were doing it at was at 70 degrees. So when you touched it was cold. Okay, in my hand it was 98 degrees, and when I touched it, it was cold, and it was boiling furiously. Okay, the water was boiling.
The pressure was very strong.
The pressure was very low. The vacuum is very strong, which is pressure low. Those are the same thing. Two ways of saying the same thing, and it was boiling away. Okay, because boiling has to do with the pressure, has nothing to do with the temperature per se. So as the pressure goes down, the boiling point goes
What is pressure?
down. What?
What is pressure?
Pressure means is how much of the atmosphere is pushing down on that item. But what happens is, if I have a pot of water, it boils when there's more pressure in the water than there is in the atmosphere. So usually in the atmosphere, there's 14 pounds of pressure. So when there's more pressure in the water, they heat it up, so that there's more and more pressure building up. Eventually, some of it escapes as steam. When it's stronger pressure in the water than in the air, then it escapes. So if we lower the pressure in the air, it makes it easier to boil out. Okay.
This is why in Denver the boiling point.
So that's what we're common. What you're used to is that in different places the boiling point of water is different. So in Chicago the water boils at 212 because we're at sea level, just about. Okay, right. Actually, the CRC is 613 feet above sea level. Okay. So
What's like Michigan?
I assume that's sea level. I don't know, but we're 613 feet.
600 feet above Michigan.
Okay, so I'm just telling you that's what the topographical map says. We're 613 feet above.
Lake Michigan, yeah.
Because it's the sea. What do you mean? What?
They can get higher than Lake Michigan.
Lake Michigan is
Okay. This is really not today's topic. But so at sea level, water boils at 212. Okay. But in Denver, which is however high Denver is, water boils at 202. Okay. And in Mount Everest, as you see on the screen here, water boils at 158 degrees. Okay. Because it's much less pressure. Okay. So it's much less pressure, water boils at a lower temperature. Okay, so again, the boiling looks the same. It's boiling. It looks like bubbles. The whole works, but it's just not the same temperature. It's not
If
the
your
same.
hand in that 70-degree pot, what do you get birds?
No, it's cold. It's not hot.
Not possible.
So you didn't see it. And if you see it, you'll believe it. Okay, I touched the thing, and it was not hot. It was cold.
Outside.
That's outside. Inside it was boiling. Trust me.
Okay, so you could believe it, but it's not true. Okay, anyhow, it was not hot. So now in an evaporator, we're going to use pressures that are vacuums that are even stronger than a Mount Everest. Okay, we're going to get the boiling point way lower. I don't know if in my examples it's going to, but maybe a little bit.
Is this like a pressure cooker or exact opposite?
The opposite of a pressure cooker. Okay, let me tell you. Cooking happens based on temperature. Boiling happens based on pressure. So a pressure cooker says if I increase the pressure,
By sealing it.
The opposite of vacuum.
right? Then the boiling point will go up. So instead of my noodles cooking at 212 degrees, I can make my noodles cook at 250 degrees. They'll cook faster because the cooking has to do with the temperature.
The water can reach higher levels.
And therefore they'll cook at a higher temperature. As opposed to in Denver, eggs take longer. A 10-minute egg takes 15 minutes to make in Denver because cooking has to do with temperature. So the water doesn't get hot enough. The water doesn't get hot.
It's not hot enough, it takes longer.
So it takes long because it's the temperature that does the cooking. Temperature does cooking, but boiling has to do with pressure. The two separate things. Okay, so we're used to living at sea level. So for us at sea level, we have an idea of how long temperature and pressure and cooking go together, but they're not
And why does elevation affect pressure?
because there's less atmosphere up there. So the atmosphere is lighter up there for whatever reason. That we'll have to ask somebody else why.
But in the Dead Sea, for example,
Right, at the Amanach, okay, where it's lower, so there's more pressure. So the boiling point is higher.
To the earth and everything like that.
I don't know. That's not my job. I have no idea. It is what it is. Okay? So we're going in our evaporator, we're going to make the pressure the vacuum even stronger and the pressure even less. And okay, now what we're going to talk about today, we're going to talk about a certain kind of evaporator, which in my mind is the most common, typical one that's used.
One more question.
Yes.
Water evaporates not because of heat, but rather because of boiling. Is that what I...
When it reaches, when there's more pressure in the water than in the atmosphere than
Right,
it
nothing
was.
to do with heat.
Well, heat is what we do to make that happen. Heat is how we make it happen.
If you
But
put a drop of water on the table and leave it out, eventually it'll evaporate.
that's separate. That's a little bit differently. Yes, because it will.
And it's not, is that pressure and it's not temperature? Why did it evaporate?
That's because really what makes things evaporate is when it's the surface. What the molecules on the surface leave the thing that's there and they escape into the atmosphere. So at regular atmospheric pressure, when the water just sits there on the floor, the surface, there's always molecules moving around and some of them bounce out. They leave. We call that evaporation. They just leave. They're bouncing out. If we make more surface area, they bounce out more quickly. Okay, so like if you take a bucket of water and you put it on the thing, it'll take a week for it to evaporate. If we mop the floor with it, we spread it thin over the whole thing, it'll evaporate in 2 minutes. You know what I mean?
You see that it does without pressure.
So some escapes by itself. By building up pressure, we make the molecules move more quickly, and they escape more quickly. That's what we call boiling. Okay, so we're going to talk about a specific kind of evaporator, which I think, at least in my mind, that's the most common that you see in food production. There are other kinds. There's something called a tubular falling film evaporator and rising film evaporators. We're not going to talk about them. The logic or the chachma behind them works the same or similar, but we're going to talk about a certain kind. The other one, as I mentioned, that we've seen, there's another thing called an evaporator that they use to make maple syrup. Nothing to do with what?
Otherwise known as
It has called the rig. It had nothing to do with what we're talking about today. Okay, I mean it's the same idea. We're boiling the water out. It's the same idea. You're getting the water out of the maple syrup in order to make it what you want to buy in the store, rather than what comes out of the tree. But it has the way it runs has nothing to do with what we do. Okay, so the main part, we'll call the heart of the evaporator, are something called effects. Okay, otherwise known as calandrias. I don't know if I pronounced that right. Okay, and in every an evaporator will have a couple of them, 3, 4, 5, however, depending on the size, we'll have a whole bunch of them. Okay, it's made of 2 main parts. Okay, a heat exchanger, a good old-fashioned plate heat exchanger, which heats up the juice, and a separator, which is basically a big empty vessel. Those are not to size. What I'm saying, the separator is much bigger than the heat exchanger. A big empty vessel where we will separate the juice that's becoming more and more concentrated versus the water that's boiling out of it. Okay, we separate it. Why are you looking at it crooked?
No, I'm saying every distiller is like that. You separate different...
No, it still works differently. No, it still works differently. You'll see in a second how this works differently.
Picture of the evaporator?
Well, it's actually the first screen that was on before you came in, and it's coming soon. You'll see a picture.
One more question. What is an effect?
An effect?
What effect being used here?
These two things together. This one unit is called an effect. It's called an effect, yes. For whatever, I don't know.
Name of the machine.
That's called the section of the evaporator is called an effect. Okay, I don't know why they call it that. Okay, now in a evaporator, all the juice goes through all the effects. Okay, it's not like some goes to the first one, some goes second, some to the third. Everything goes from 1 to 2, 3, 4, 5. Each one moves from effect to effect. Okay, so now I'm gonna show you in diagram before we get to a picture. And a diagram, what it looks like, okay, what's going on in the effects, okay, because here, and you'll see the chachma of what's going on, okay. So here we go, we started with just one heat exchanger, okay. Remember that looks like that's the heat exchanger, okay. That picture, that's a heat exchanger, okay. Those are all the plates. If you can't tell, those are what? Why are they crooked?
The lines, don't they go...
No, those are the plates. Those are the plates going down. Okay, this is my artistic ability. Okay, and yeah. So this is a heat exchanger. Okay, this is our first. This is the heat exchanger, the first heat exchanger in the first effect. Okay, the heat exchanger in the first effect. Okay, and what is it? There's product coming in on the bottom, the product coming in on the bottom, and steam coming in on the top, and they heat each other. Okay, that's a good old-fashioned traditional heat exchanger that heats up the juice. Okay, water. What'd you say?
Is the water on the outside of this?
No, the steam on the side, okay?
Sure. Typically it's water.
It could be there's water. It could be water.
Just trying to hear what's the feeling.
I don't know what there's no chug. In what I'm used to, evaporators, their heat exchangers are powered by steam. I might be wrong.
But I'm just curious. Okay, I'll talk about it a different time. A plate in this type of heat exchanger will work just as efficiently with steam?
Yeah, why not?
Okay.
We used to, okay, if you would like to, you can put water if you'd rather put hot water, you can put water.
You can use a tube and shell also. Just trying to heat it up.
You can do whatever you want to. Yes. I'm just telling you what I think is normal. What the way you would do it.
This part has nothing to do with evaporation. You just trying to heat up the meter.
You're going to see, just wait, the picture's going to go across the whole screen. Okay, for now, I'm just starting. Give me a second. Okay, so we put in juice, which is hot or preheated or cold juice, whichever. Usually preheated, juice comes in, and it's heating up in the first heat exchanger, okay? Then it goes, condensate comes out of the bottom, okay? We of course, the condensate comes out because of the steam, and then the juice, the hot juice now moves into the first separator. So what happens is, in the first separator, it comes in, as you'll see in the picture from the side, okay, it comes in from the side, and this effect has a little bit of vacuum to it. Okay, there's vacuum in this effect. Okay, however, we're not talking about that, how they create the vacuum. There's vacuum in this effect. So what happens is, when the juice comes in at 195 degrees into an effect that has a vacuum on it, what's going to happen? It's going to boil out. Okay, water's going to boil out of that effect. A certain amount of water boils out because at 195, it's already at the boiling point for the juice in that effect.
You're saying that it's already separating while it's going through the...
As it hit, no. And here, it's just hot. There's no vacuum.
Escape for the water.
There's no vacuum in the heat exchanger. There's no vacuum in the heat exchanger. But when it gets into here, into the effect, there is a vacuum. So when it hits the vacuum,
so there's no vacuum in the heat exchanger.
Right. There's vacuum in the effect. So when there's vacuum in the effect, the 195 degree juice hits there, so it starts boiling.
Right.
So the juice, which is comes in from the side actually, and it spins around, and as it's rolling down to the bottom, as it's spinning around the effect and rolling down to the bottom, water's boiling out of it. Okay?
So you're saying there's bottom from that one thing.
You're going to see, you're going to see the bottom in a second. Okay, so what is it's spinning around as it's spinning around it's a round like tube. As it's spinning around it's water's boiling out of it. Okay, because it's under vacuum and water's boiling out of it. Okay, now it's just centrifugal force. It's coming in sideways. It comes in sideways, so it just shoots it like this, so it spins around.
Just go around the bottom of the...
It's like a tall cylinder. Okay, so as it spins, it's coming around from the middle, so it just spins around like this. It rolls down to the bottom. The point being is, as it's going around and around, there's a lot of surface area. Okay, it's running itself around the edges, so the whole inside is like open.
It's filled or no?
No, it does not get filled. No, it's draining at the bottom. It's like a cyclone. Yes, like a cyclone.
Whatever's left over goes out the bottom.
You're going to see the bottom in a second. Just wait. You're going to see the bottom in a second. So it's spinning around, and the water's boiling out. Is boiling out.
And the water's boiling out of steam.
It's steam. Yeah, it's steam.
The light blue is steam. It's not.
That's supposed to be steam. Right. The blue as in water vapor, kind of like purple as in like grape juice, and blue as in like steam vapor, like that. Okay. So it's the steam is boiling out. And there's something called evaporative cooling, which is to say when things boil, the liquid that's left behind, when you take a liquid and you put it into a situation where some of it boils, the rest of it cools down in temperature, like you see in a spray dryer. Like, when you Kashrus a spray dryer, you pour water that's 212, and it comes out 150 on the bottom. It's something called evaporative cooling. Okay, I'm not going to explain it. Okay, just believe me. So when the
energy of the heat went into the
okay, wonderful. So good. Okay, so what happens is, so out of this, we have steam rising to the top and juice that's a little bit concentrated, lost some of its water going down to the bottom. Okay, now what happens is that steam and water join each other in the next heat exchanger, which is part of the next effect. Right. So the juice that's coming out of here, the partially concentrated juice coming out of the first separator now becomes the product for the second heat exchanger, and it's heated by its steam. His brother, who just boiled out of it a minute ago, the steam that boiled out of the top there is now coming and heating this juice in the second heat exchanger.
Just to be efficient.
This is a complete for efficiency. The only time you add energy is in the first one. The only that's added is the steam in the first one. Everything else it goes for free. Okay, everybody else goes for free. Yes.
How high is the steam?
You're going to see the steam over here is 195.
If this is my very rudimentary understanding over here, if it's 195 when it went in there, right? So that means that there's some total of heat that you could gain is 195. So that means that
okay. So no, incorrect. It's true. It's only 195, but we could. No.
Steam by definition is 195.
Right. No. The steam is 195 degrees. The steam is 195 degrees. It's under vacuum, so it boils at less than 212. It's under vacuum, but this is an ikar in understanding steam. In order to turn water into steam, there's temperature, so it gets to 195 degrees, and then there's something called latent heat. Okay, the important ikar for heat for steam. 195 degree steam has in it about 800 degrees worth of heat in it that doesn't raise the temperature. It's called latent heat. It's bekoyach. Okay, it's not bepoil. Okay, bepoil it's 195. Bekoyach it's about 1,000 degrees. Okay, there's this energy called latent heat that's sitting in there. In order to get water, energy, yes, to get water to go from liquid to boil, after we get the water in our house to 212, you have to hit in about another 800 degrees worth of temperature, what we call BTUs, into it, in order to get it to convert from a liquid into a vapor. All that energy is inside the steam that's coming into the heat exchanger. Okay, so it's coming at 195, but it's carrying the power of be'erach 1,000 degrees. Okay, so has a lot of.
And the steam could carry.
The steam is carrying a lot of energy, which is not going to give over to its juice brother which just came out of the first effect. Okay?
How hot is the steam?
The steam is 195 degrees, but it's heating as if, so to speak, as if it was 1,000 degrees. Okay, it's giving over energy into the juice. It won't make the juice more than 195. It can't, but it can give over. It can do a lot of heating to that juice that's coming out.
What the latent's going to do?
Yeah, the latent transfers very easily. So latent heat transfers really quickly, really easily. So latent heat transfers, that's why you use steam heats really quickly.
So the mice, it's only 195.
But it's 195 with lots of energy behind it. Okay, so it's the same Lamaisa as your thing that you weren't going to get. That one is boiled. Okay, anyhow, so what happens? So in the second effect, the same thing goes on. Okay, and the water condensate comes out the bottom. Out and the water, the juice that goes into the second separator is not as hot. Now it's 175. Okay, it only got up to it got to 175. But the juice that came to 175 over here is now even more concentrated. Okay, because in the second separator, the vacuum is stronger in the second separator. Okay, it's even stronger than the first one. So at 175, water boils out, and now juice spins around and comes out the bottom again, more concentrated, and then.
Latent energy important to this.
Yes, that's what makes it be able to boil. That's what
Kashrus we ignore it. The fact is,
no, we can't, no, we don't ignore it. We need to know that it exists because it's
we don't reckon with that.
You don't have to reckon with it in Shulchan Aruch. You have to just know that it happens to understand how things work.
You wouldn't check out the lettuce play or anything like that.
No.
If you want a kashrus, you have to know. That's what I'm saying. For kashering, you don't have to know.
No, you have to.
You have to know how to kasher.
So
we look at whatever it is in the mindset.
No. For kashering, we just need the temperature. You need to know it to understand what's going on in the machine.
You have to get the temperature. You want to know how to get the temperature. You look at the temperature.
Okay. Anyhow.
It's not going to be a problem.
Okay. So now we go after the second effect. Guess what? The same thing happens again. So
when they try to do it, why can't they just do it under the extreme vacuum and just do it all at once? Is because it's
efficiency. No, it's efficiency. It's efficiency. This way we only have to put in the steam once, and we get all this done by just heating it once.
If they would lower the vacuum, if they would make the vacuum even more intense. In the first one, then the temperature would be much lower, and then if the temperature
that would be more complicated. But that wouldn't. So in a falling film evaporator, we do something like that. Okay, but that's not what goes on here.
Okay? Why? Just because when it's gradual, it preserves the flavor.
That I don't. No flavor. We'll get to it in a second. We didn't get the flavor yet. Okay, I'm not sure. I don't know the answer to that. Okay, so then we go to our third effect. Okay, and the same thing happens. Okay, again, here the juice got even lower temperature. The vacuum's even stronger. And this is, you see I'm at the end of the screen. So this is our last. And
the condensate never returns.
I'm going to get into the condensate in a second. I'm going to get to that in a second. So we get to the third effect, and in the third effect, our juice is now even again the vacuum is stronger. In our case, the last evaporation is happening. So what happens is steam goes out the top. Okay, steam boils out the top, and our finished concentrated juice comes out the bottom. Okay, so now we've done it in each effect. We got a little bit of water out until we got to the last one. By that point, we've gotten as much water as we wanted out. We got all the water out that we wanted to, and our water is concentrated. Okay?
Yeah, I have a company that does this, and I never thought what was going on.
That's why you came to me. Okay, so that's it. Okay, so here now.
So that is to make concentrated juice. Is that the idea?
To what?
To make concentrated juice.
Well, to juice, or the other example we're using is to concentrate milk before you spray dry it. So the point is, you're getting rid of the water, So either because the juice you want concentrated juice, or in the case of milk you want that. So rather than have the spray dry get out all the water, you concentrate the milk first, so that as a step before spray drying, it makes it easier to do spray drying. So let's concentrate anything else. You want to get the water out. That's the whole point here, is to get the water. You're concentrating it by getting rid of the water. Okay. So now this is the picture that was on the open screen, and that like this. Okay. In this picture, you're looking at 4 effects. Okay. You're not seeing the heat exchanger. Okay. You're just seeing the separators, or the calandrias you want to call them. Okay, here's 4 of them. Okay, the 4 calandrias. I don't know if I pronounced that correctly. Okay, these are these are the 4 effects in this picture. Okay, in the red box over here.
Not in order the way they.
Yes.
Supposed to go. The 1 is the first one.
Yeah. Well, order's like 1, 2, 3, 4. That's how. Yeah.
The last one is the first one.
Correct.
Why is there an invitation around the milk?
I'm about to show you. So I'm about to show. That's what the red box. I'm about to show you the red box. That's the juice coming into the separate to make it spin around. I told you it comes in from the side. It comes in from the side and then it spins around. So the juice in this, I don't know if this case was juice. The juice that comes in is coming in this way sideways.
Wide?
In this case, it's very wide.
So they want to make more of a...
They want to spin around.
Yeah, but the surface is good, right? The increase you want to make an increased surface.
Yes. So this is the juice comes in sideways into in the red boxes you're seeing is the juice coming in, is where the juice comes in. Okay, and then on the top is where the steam, the top picture didn't come out as good. So the vapor coming out. Okay, that's the vapor boiling out of the top, and it goes in like an upside down letter J. Okay, boils out the top and heads down to hit the heat exchanger to go into the next one. Okay, the heat exchanger is on the back.
I need so much space on the top.
The top is where the boiling is happening. That's where the vapor is. Okay,
and you need a big section because.
It must be a physics thing. I don't know why. I don't know. So the water, that's where the vapor is boiling out and heading out the top. Okay, so this is all what they look like. I mean, give or take.
So it's coming. The steam is going out into the next.
Out the top and
into the next thing.
Behind, what we don't see behind here are the heat exchangers that are feeding the next one. So it's coming out of the second one. This one coming out of the second one. You see, you can see a little bit that it bends down. It's like a J, an upside down J. It bends down, goes up here, up into the green. Behind there, right? It bends down, and then there's a heat exchanger between 2 and 3, and that heat exchanger feeds number 3, and then number 3 comes out.
And the pumps on the bottom. What are they for?
Is that maybe moving the juice from one side to the other? I don't remember. I don't know. Maybe that's moving the juice from the second one to the third. I don't know. Okay. So while we talked all about the evaporating and how the evaporation part of it is going on. Okay. While we talked about all of that, you noticed I kept mentioning that there's condensate coming out of each thing. Okay. And the reason why I mention that is because it's important for us, okay? And I kept mentioning it so sort of get you to realize that it's important for us to know. I'm going to go back to you'll see it better. Okay, to this picture. This condensate comes out of each one of these heat exchangers. Okay, the heat exchangers are using steam to heat them up. Okay, the guys argue that no, they want water to be in the first one, but for sure in the other ones there's going to be steam coming. Is what's heating it. So there's condensate coming out of each of them. Now, the condensate coming out of the first heat exchanger is good old-fashioned condensate, like any other place in a factory, and they could send it back to the boiler. They can do whatever they want to with that condensate. That's a good old-fashioned condensate, like in any other place. Okay, the condensate coming out of the later effects, the later heat exchangers, can't go back to the boiler.
Because it's juice.
Because, well, it's not juice. It's really water, but it has carryover of juice in it. It does have carryover to it. So that's not going back to the boiler. Okay, you're not going to send that back to the boiler. Okay, so what's going to happen to the condensate from those other ones? Okay, what's going to happen to it? So there's a few choices. Okay, one is what people have mentioned, and that is like this. We'll make hint to that, which is when you boil juice to evaporate it. Okay, when you boil juice, not only does the water boil out, but the flavor boils out also. Okay, the flavor is more volatile. That's the word you use. It's more volatile than the water is, so the flavor boils out very quickly. When you heat up water in your house, like in a pot, someone mentioned, you're going to lose the flavor of it, called the flavor essence. You lose because that stuff boils out really quickly. So when you boil, in particular, at the second heat exchanger, at the first effect, you're going to be boiling out water with a lot of the flavor. So the condensate coming out of that second heat exchanger, which is basically it's the vapor coming out of the first effect, that vapor, you want to capture that. If it's juice, if it's something you care about the flavor of it, then you capture it and you send it to a distillation column called an essence recovery system, where you take the condensate that came out of there and you distill it to separate the essence, the flavor, from the water, and then you take that essence and you put it back into the juice. So if you make concentrated grape juice from concentrate, it means is you concentrate like this, you concentrate the grape juice, but you capture the essence from the condensate that you have in order to put that flavor back into your grape juice, to make your grape juice taste like something.
Into the concentrate.
Into the concentrate. You put it back into the concentrate so that the concentrate will taste like something. Okay?
For some reason, grape essence does not smell. Because I've never tasted it. It does not smell like grape.
It does not? What does it smell like?
I don't know.
Okay. But,
It smells very good.
okay, well that's what it's for. Okay, I don't know. That's what it's for. So like in other words, the difference between a higher quality or a lower quality juice from concentrate is how much essence they put back in. You don't have to put in as much as you got. If you got out 1 ounce, you could put in back 2 ounces, or you could put out a half an ounce. You could put nothing.
That's the most valuable part.
That's correct. So you deciding it, depending on how good you want your juice to taste, will be how much you put back in. The essence is more valuable than the concentrated juices. You put it in as you want. Okay. So when I'm off topic, but if you make a Mazonis roll and you use apple juice in it, okay, and you use apple juice from concentrate. So part of the reason why it doesn't taste like apple juice is because you use the cheapest apple juice you can, because you're just doing it so you can tell the rabbi that you put in apple juice. So you use the cheapest apple juice, doesn't taste like apple juice, okay? It's apple juice, but it don't taste like apple juice because you get the cheapest one. The cheapest has the least or the non-essence in it, and therefore it doesn't taste like apples. Okay, anyway, that's a sorry point.
Is the apple juice concentrate or what?
It could be apple juice from concentrate. Apple juice from concentrate is legally good.
They're like apple. But they're going to put in water too.
No, concentrate, if you don't put in essence, will taste very little like apple. The flavor boiled out. The flavor out for the water, you just put in good water, not flavored water. Okay, so one thing you do with condensate is you send it to essence recovery. Okay, that's one thing you do with it. Okay, another thing you could do is you say is...
You got a picture of that? Where is the columns?
Yeah, it's a regular distillation column, nothing special, but it would be in a juice plant, it would be there for the essence recovery. That's what it's in. Juice concentration plant, it's for essence recovery. So, that's one thing. And there's another thing you can do with it, and that is like this. Let's say you're making milk, okay? There's no essence recovery from milk, okay? No one's getting back flavor from milk. So you're just boiling out milk, okay? So you're doing salt or whatever other thing you're concentrating, and you don't care about it. You're not trying to capture any flavor out of the condensate. Well, you have this hot water. You can't send it to the boiler. Okay, so you could pour it down the drain if you want to, yes, but there's better things to do with it. Let's say on the other side of the plant, you have something that needs hot water for its process. Okay? Let's say you're making something else that needs hot water in it. You need hot water. So here's hot water that's there. It has a little flavor to it. Who cares? It doesn't bother anybody. So you need hot water in the plant. Why heat up new hot water? Take the hot water from this condensate and pour it into a vessel in another part of the plant. Or what happens if you need to preheat something? Like what happens if you need to preheat this juice coming in? Okay, you need someplace hot water as a preheater. So this stuff could be hot water is perfectly fine to be used as a preheater someplace. Okay, in other words, you want this hot water here. You could pour it down the drain, or you could use it someplace else in the plant, or you could use it as your first rinse in your CIP. Your CIP first rinse doesn't have to be great, but you need hot water. You want hot water for it, so you have free hot water coming out of here. So why let it go down the drain? Send it to your CIP tank and let it use that to use your first cleaning of your equipment all around the plant.
The temperature's not going to be very high.
Whatever it is, it's better than the city water. It's free. It's there. So if it's not worth it, you let it go down the drain. But if it is, if you have some use for it in the plant, then why not use it? Okay. So
Condensate for number 2.
Just using it to wash out.
It'll be plenty hot.
It's free water. It's free water.
That's hot water. Okay.
Warm water.
Yeah, it's whatever it is. Okay, so that's called in the industry. That's called cow water. Okay, that's stuff that comes out of this condensate that you can't send back to the boiler, but it's hot water that's condensate that has uses in the plant called cow water. Okay.
What is from grape juice? What do they call it?
I don't know. In my mind, they call it cow water. Okay. So now, and then that has the status of whatever it came from. Okay. So it's a truvas rush about cow water. Okay. Steam from a milk, or truvas reverse from grape juice. Okay. So it has the thing of what it came from. If we were concentrating grape juice and it was stam yayin, then that condensate is stam yayin. If we're boiling milk and what comes out of it is milk. Okay.
Is that a finish? Yeah.
It's Pashatiyah. It's a Shiloh Rishonim.
What's Shiloh?
What's a Shiloh? It was a new thing. It was something new that came up. It was something new that came up in about 1,000 years ago.
Saying the Shiloh is when it evaporated.
Does it? Well, what happened? The reason for the Shiloh is because we talked about with the alcoholic beverages, if you're curious. But the Shiloh is that when it's a vapor, it's not us. So now it went from a liquid to.
Why didn't it also when it's a vapor?
What do you say?
Why didn't it also?
It's not. It's invisible. There's nothing there. It's an invisible thing. What do you mean? There's nothing here. It's an empty pipe. If you look at it, there's nothing in the pipe. It's a blank, empty pipe. So you say a lot. So there's magical water coming out on the other side. Okay. Anyhow. Okay. So now.
Is it the act of chol, what does the machine is found? Is it not of?
No, it has a dinner. It's a riot from a mission in Pulyam, I think it is. I don't know. They bring a riot to. Yeah. Okay. Not for today, but anyhow. So. Okay. So. What that the reason why I told you that aside that it's interesting and you should know what goes on is that means is that if there's an evaporator in the plant, that even if the evaporator is not used for kosher and treif, or even if the evaporator is not kosher altogether, not under Hashgachah, the what's going on in the evaporator affects other things going on in the plant. You have to care about the cow water coming out of that evaporator because it's used other places in the plant. And I'm going to give you two examples. Okay, two examples. There was a plant that at least one person here knows about. Okay, and this company needed to wash. They had raw potatoes coming into the factory, and they needed to wash them in hot water before they made it into potato starch. Okay, and the potato starch part of the plant was simple as anything. Okay, there's nothing complicated going on about it. They're taking potatoes and turning it into potato starch. Okay, and they need to wash it with hot water. Way down the line, in another part of the plant that did not have hashgachah to it, they were concentrating something to do a protein product in another part of the plant. Okay, there was an evaporator in the other side of the plant, and it wasn't under hashgachah. They said, we have this great idea. We have all this water coming out of the condensate coming out of the evaporator. We need hot water to wash our potatoes on the other side of the plant. We got all this hot water right here. What, we need to make up our own hot water. We got hot water over here that we can take from over there and bring it to this side of the plant to wash our raw potatoes coming into it. Okay? What? It was however hot coming out of the evaporator. So the different stages is different amounts. The point was, so the point for that company we said to them was, that protein side of your plant needs to be under Hashgachah, not because you could care less whether it's certified, because we need to keep an eye on that evaporator to make sure that the water for that washing your potatoes doesn't make your potatoes straight. Okay? Yeah, you're too rabbinic. We get about cliche to them. We can't have treif hot water going on the kosher potatoes. Yeah, you could sit at home and think about this. Okay, yes, okay. Another example. Another example. There was a company that if I remember the details correctly, they needed the kasher from chol of stam milk powder to chol of yisrael milk powder. Okay, so they had a kasher. They had a kasher the kelim to go from chol of stam to chol of yisrael. Okay, so they went to kasher, and when kasher, however they worked it out, they started with the CRP system. Okay. And then someone realized that the CRP system is fed with cow water. Okay, so they were going to, that means to say is, if you would follow the procedures the way it's supposed to be, they'd be kashering the chol of Yisrael equipment with chol of stam water. Okay, that wouldn't exactly do the trick, you know. The rabbis could think about that even more, that could work, but that wasn't obviously a very smart idea. Okay, so we've talked about how the machine runs. We talked about being aware particularly about the condensate, again, because you care about the condensate because it spreads around the plant in ways that might make a difference. And now I'm going to talk about Kashering. Oh, sorry, go through the slides again. Sorry, guys. Okay. Oops. Okay, so there are three big things to think about when we think about Kashering the evaporator. First is, the ikar din is, you're allowed to kasher kabbalah kachpoltai, the same temperature as the product was, but the minig, when some of the places can say this, to always use roasting. Okay, so we would like, if we can, to do roasting. If not, we'll be satisfied with kabbalah kachpoltai. But in doing kabbalah kachpoltai, we have to remember that what I said at the way beginning, that this whole system works because the water boils at a lower temperature than the solids that are in there, at a lower temperature than the milk solids or the grape solids that are in there. So if we run the machinery exactly the way it was used during production, And when kashering with water, the water is not going to get the same temperature that the product was, because the product runs at boiling points of grape juice or milk or whatever that was in there, or soup or whatever was in there, which is at a higher temperature than what we have. I'm saying like grape juice boils at 214, 215 degrees, okay, or the solid. Or as it gets more and more concentrated, the boiling point actually goes higher and higher. And if we run just plain water, it's not going to be that temperature, okay. Therefore, if we're saying we're just doing Kabbalah Shem,
but if it's boiling, even though it's lower temperature.
No, because kashering does with temperature.
You know there's problems with that. There's all kinds of problems with that.
There's problems with that?
Yeah. That means you're telling me you take a keli that became treif in Chicago and kasher in Denver. Whoever said something.
So we took that about 1,000 years ago, but the truth is that those are all considered roasted. They're all at temperature. So if you take it to Tibet, then you have a problem. So if the guy's backpacking in Tibet decides, I bought a treif kli and now I was chayzer b'tshuva and I decided on top of Tibet to be kasher, then I potentially have a kasher. Yes.
Because what's the better problem with Denver?
Oh, because in Denver it's still roasted. There's close enough to roasted.
High pressure thing.
So no, we never need to go. We don't never need to go over roasting. But so even let's say if you fry something in your house, oil is much hotter than 212. So you don't have to get roasting as the max. Okay, that's They do. Contemporary price considered. We said this many years ago.
Anybody ever has said you can kasher it boiling? End of story.
What?
You can kasher it boiling. End of story. We don't pay attention to the temperature.
Because No, because that idea that we could create a vacuum and boil things at 150 degrees is a modern invention that didn't exist. The Messiah didn't have that. So what did he think about what happened when I went to Tibet? He didn't think about going to Tibet. Okay?
Where's Tibet? I know you're talking about Tibet. What's Tibet different than Denver?
Denver's right.
Then, and what? So, the guy did.
That is big difference. That's more than the big difference.
No.
Over 200 degrees.
Okay. We will. It's a totally different story. I'm sorry, guys. We mentioned it. Okay. I'm not sorry. I mentioned it. I'm sorry. We got into it. Okay. Second is, okay. Another thing is, we only kasher. We can kasher things that were used with zaya through zaya, and things that are used with water through water. We could use water where we had zaya also. We can't use zaya where we had water. Get it?
Doesn't mean that the zaya does not turn into water.
Unless the zaya turns into water. But if it's zaya by itself, we can't use zaya to kasher where there was a thing that needed to be kasher with water.
So water kashers everything, but zaya cannot. But
correct.
Zaya does not.
Ramosha says logically, you should zaya is even stronger because it has latent heat in it. He doesn't say that latent, whatever, but it's even stronger. As far as it should be, but we're not sure, so we don't do that. Okay, that's what Ramosha says. Okay, now, so when we think about the parts of our, okay, I'm going to give you a little one. Okay, here's a mini because it's going to fit in here. When we think about which parts are the parts that need water, okay, which of the sides that needs water, okay, so basically it's everything in this picture that was purple, okay, wherever the product went, those need to be kashed with water. So in each of the heat exchangers, it's the product side of the heat exchanger, and in each of the separators, it's at least the bottom part of the separator, are the parts that touch water. Those are the parts that need to be kashed with water.
Why? Number 2 and the heat exchanger 2 and 3 had product on the other side.
No, it didn't. It had steam on the other side.
Steam of product.
It had steam. Was it a liquid or was it a vapor? What was in there? I'm talking about what has to be liquid or vapor. So on the product side of all the heat exchangers and the bottom half of each of the separators needs to be kashed with liquid. Okay. Now you'll tell me, well, what needs to be kashed with steam is the top parts. Okay, and the media side of all the things. Okay, it's not so clear. Water does spray around a little bit. It's not so clear, but we're going to work with an assumption that those parts get kashed with steam, could be kashed with steam, and the other parts, the purple parts, are the parts that need to be kashed with water.
It would seem to be pasha. They just have to mimic what you usually do.
So
it's a lower temperature than the water and grape juice.
Correct. If we just run water, we're not going to get the same temperatures that we had during production, because the water boils at a lower temperature. If we do everything the way it was,
increase the vacuum.
So I'm going to talk about that. That's what I'm coming to. I'm just leading you up to it.
Kasher with kosher grape juice.
with shamashkin, we can't kasher it either. Okay, now,
So again, the problem you're saying is what? You can't use just water? You can't just put in water?
if you run water, say turn the machine the way regular and run with water, it's going to be a lower temperature than the product was. So we're trying.
You're saying it'll be water
Certain
there?
rabbis over here.
Lower temperature?
Yes, because at X level vacuum, the water will be boiling. It's going to be boiling at a lower temperature.
I'm still not getting what you're answering me. I don't know. That water is boiling as well, just like you said with oil. So why is this worse? Because it's in a vacuum.
No.
Who's thrown up this home over there?
So I'm going to ask you to pause that. We'll talk about that afterwards. I'll tell you. You don't have to agree with it. You don't have to agree with it. Okay.
Apparently you're not the only one that said it then.
I didn't make it up.
I understand.
Okay. So now let's remember, of course, also that we want to make sure the regular things like our water, it's any ben yomim, we don't do kasher with cow water. We have to run our machinery for long enough to have to find us makaris. These are like little things that's sort of traditional kashering things we think about. Okay. Now, so what are our choices? Okay. So I'm going to show you two choices. Okay. One is the easier choice, which is not as good, and one is the more complicated choice, which is better. Okay. Okay. First choices. Raise the set point of the heat exchanger. Okay, so people said just raise the amount that you want to do and lower the vacuum and separators. Okay, so if we raise the set point for the heat exchanger, for the first heat exchanger, that's the one we can control directly. Okay, we could say, steam, we want you to hit it at a higher temperature in the first heat exchanger. The water going through the system will now be a little bit hotter than it was, which is to say is close to the temperature of what the juice was. Okay. And if we lower the vacuum will also increase the temperature. Okay, lowering the vacuum means instead of it boiling at, let's say, 195, we had before to boil at 200. Okay,
They lower the vacuum as in making it less.
Lower the vacuum.
No, yeah, it's confusing.
Okay, well that's okay, whatever. So we make the vacuum less. Decrease. Okay, so that will work. Now that will work, and it'll do everything we wanted it to do, but it will be doing it at Kabbalah Kach Poltei. Okay, that's fair. Okay, but that's not preferred.
What do you mean?
It'll be about Kabbalah Kappa. I mean, it won't be Roischen.
Lower and lower and more.
Right? You can't get Roischen into the later ones. Okay? You can't get Roischen into the later ones. But it'll be better than we had, and Mikra, then it'll be fine.
It always goes down.
Because the temperature keeps going down as you go from effect to
But
effect.
as long as you're doing it.
So it'll be Kabbalah Kach Poltei, but it won't be Roischen.
It's more steam into heat exchangers. The other one.
No matter how much you're going to pump into here, it's automatically going to be...
Can you introduce steam to 2 and 3?
No, you can't. They're not made for that. They're not... Okay, here we go. So now, we have another option. Okay, and option number 2 is it's going to be in 2 stages. Okay, and the first stage is going to be the same as the other one. Okay, and what we did was we kashered as much as we could of the other one. Okay, now for our second stage, what we're going to do for the second, what the goal of the second stage is to get our water temperature to be even higher. But what's going to happen is like this: if we make the set point in the first heat exchanger to be 212, okay, we make it as hot as we can make it, and we completely turn off the vacuum on all the separators. Okay, we turn no vacuum on the separators. So what's going to happen? The water that we're using for Kashering is going to start off at Roischen, and it's going to go from effect to effect at Roischen. Okay, it'll probably lose a little bit of temperature as it moves along, but give or take, it'll be going through the whole thing at Roischen. Okay, and that's great. We love to have Roischen water in all the places. What we're going to lose is there's going to be no evaporation, no steam. So the tops are not going to get kashered, and the vapor side are not going to get kashered. Yeah, it'll spin around, but what's going to happen is there'll be no boiling, and there'll be no vapor. None of the vapor sides will get kashered, not the top of these separators, and not the other side of the heat exchangers.
It's flying through 212 and there's no steam coming in.
A little bit, there'll be a little bit, but presumably not enough to kasher. But the point is, we covered those in our stage 1. Okay, stage 1 kashered all the parts that needed vapor as much as we could. We did what we could for that. But the second stage point is we're getting boiling water to as many places as we can, so we have that extra. That's what we get advantage of these. Because of Zaya. No, it had Zaya of how hot vapor sitting it. You could call it Kisuk there if you want to. You can call that. Or just because
also the second one, not the machine.
So it's an in-between, because what it is it's not the finest Bakaras. It runs for 10 hours straight with stuff going through it. So it's between a cliche and a cleavation. That's what we say, because it doesn't have the finest Makaras, so it doesn't have the lower status of a cliche. It's close to a cleavation.
It does or does not have?
It does not have the finest Makaras.
It doesn't have the cooler.
What?
The walls were cold before.
Well, the wall, no, but after we run it for hours, the wall,
His point is if we make it anonymous, so now it's cold.
so when we did our first stage, we'll have preheated it. So I mentioned in quickly was we have to run it for long enough to have no more definers Makaras. We have to do that to gain that advantage, to not definers Makaras.
In the Kashering, you do it for them?
In the Kashering, we run the
When
Kashering.
they do it,
They do it, it's not.
it's hot or it's cold?
It's not.
Well, the first minute it's cold, but after 15 minutes it's not cold anymore.
It's going to be hot.
So we have to run our Kashering for long enough. That was one thing I said so quickly was the regular Kashering issues, which you have to make sure we do things like that for regular Kashering reasons. Like make sure we don't have definers Makaras. Okay, now there is such a thing, I'll just throw in, there's such a thing, there are people who who clean their evaporators with spray balls. Okay, and they actually spray ball on the inside of it to clean it. Or they even fill it up. They could close the bottom up and fill it up with a lot of water and chemicals and clean it up. Okay, that will do a fine job and potentially could be used for Kashering, but typically that's not going to help you for the steam side of the heat exchangers. Okay, so we have to think about those sides also.
Spray ball wasn't tough.
It could be, but la dafka is it going to be?
If you fill it up, it'll overflow.
So yes or no, you have to pay attention to what's going on. It's not designed to do that. It could be used. I'm saying it's a tool potentially. Okay, but
Do they have their own CIP, I'm assuming, if they want to switch from grape juice to milk, or whatever, I mean, right?
CIP is CIP. No.
No, but they have their own cleaning system, so you're saying it's not designed, I'm just wondering if why would it be designed to have?
Cold do with cold water and chemicals in the happy.
Okay.
Okay.
To say to people.